Brother student. Oh, now we are at 26 because we were 26. So every morning I will open the room at 10 minutes to 9. So don't come. So do not come earlier. So because it's I must be the first one to enter in the room. Okay. Now, guys, I started recording. Yes. Do you have something to say? Okay. So now, guys. Now we continue with yesterday lecture. At least, let me see. Well, if you remember, yesterday we concluded the lecture by introducing elementary function. In particular, the last function we saw together were exponential function and logarithmic function. Now, these are the last elementary function. Yes? You see? If you have troubles, turn on your microphone, guys, so I can hear you. Is it everything okay?
Yes.
Okay, thank you, guys. You see, here, if you read at page 12, we arrived here yesterday. I wrote insert file, this file. We have, if you open the folder I uploaded or I gave you, we have a file containing some very few example of equation and inequalities of exponential and logarithmic type. So we are going to solve only to do a short review of inequalities and equation of exponential and logarithmic type. So now let me, so if you go on crash course, no, you don't have this one, you have this folder because I gave you only this one for the moment. You see the first file is ecl-nec-exp-log equation. Okay, so if you open now, I increase the dimension. So solve the following equalities and inequalities. These are very simple, but only as a review if you don't remember them. Someone is saying something? No. Okay, so suppose you need to solve this very simple equation. 2 to the power x equal to 1 over 8. This is an exponential equation because you see 2 to the power x is an exponential function. So x is the x at the exponent. So the unknown we want to find is x, which is at the exponent. So here I show you a couple of methods to solve them. For example, a couple of ways. For example, you see the second side, rewrite the second side in a convenient way. For example, you know that 8 can be written as 2 to the power 3 because 2 times 2 times 2 is 8. So you see, I wrote below 2x equal to 1 over 8, which is equal, 1 over 8 is equal to 1 over 2 to the power 3. Now, you remember that if you want, you can, if you change the sign of the exponent, as we saw yesterday, you can do it, but you have to take the reciprocal of 1 over 2, which is the reciprocal of 1 over 2. So you see 2, I changed the sign of the exponent and I took the reciprocal of the basis, 2 to the minus 3. In this case, guys, so this is our equation. Well, if you look at this equation, you see that the first hand side is a power with basis 2. The second hand side is a power with basis 2. Two powers with the same basis are obviously equal if and only if their exponents are equal. So in this case, you can write x directly, x equal to minus 3. Okay, this is the intuitive way. Otherwise, we can proceed by steps by using the relationship we saw yesterday between exponential and logarithmic function. I mean, by using the property of the exponential and the logarithm we saw yesterday. In particular, guys, this is this is a specific way to solve. So, and I did it because I simply understood immediately that this could have, I mean, that A can be expressed, could have been expressed as a power with basis 2, and so I realized that I could have applied this property, this approach. However, the more general, which work always, is the one I'm going to show you. This is the more general, so again, solve it in another way. 2x equal to 1 over 8. So the more general is the following. You see, x is at the exponent. Solving an equation means that you want to find at the end of the story x equal to something. So using poor words, I'm saying we want x to fall down at least, because at the end we need to find x equal to something. So we want x to fall down. Here is the trick. You have to take, you know, that if you take the same operation to both sides of an equation, the result of the equation is not affected. So the operation we are going to take of both sides is the logarithm. In particular, guys, which is the basis of this exponential function, is 2. So it is convenient, if you want to make x to fall down, to take the logarithm with basis 2. Then you will understand in a moment why it's convenient if you don't remember. So take the logarithm with basis 2 of 2 to the power x. Obviously, since I took the logarithm with basis 2 of the first hand side, I have to take the logarithm with basis 2, again 2, not another basis, of the second hand side. So this equation can be written equivalent in this way, because I perform the logarithm transformation with basis 2 of both sides, so the result is not affected. But now, remember that yesterday we did all these stupid exercises. I mean, for you, for some students, probably those exercises were stupid, but they were, on the contrary, very important to make practice with the property of logarithm, because yesterday's exercises were even more complicated, at least someone. Now, and remember the property and that we applied yesterday. Look at the first hand side. X is the exponent of the logarithm. Remember property C, the exponent of the logarithm. We applied this property at least 10 times yesterday, but probably even much more. The exponent of the argument of the logarithm can be written as a multiplicative term in front of the logarithm. So you see x times logarithm of 2 with basis 2. So you see that by taking the logarithm with basis 2 of 2, we got in reality two results. We make x to fall down, as we wanted. And secondly, it was really a good choice to select logarithm with basis equal to this number. Why? Because now we have logarithm with basis 2 of 2, and we saw this property several times yesterday. This is equal to 1. I mean, if you take logarithm with basis 3, for example, of both sides, you still make x to fall down, but then you have logarithm with basis 3 of 2, and it's not so useful. On the contrary, you see that if you take the logarithm with the same basis as the basics of the exponential, then you don't only make x to fall down, but you have then times logarithm with basis 2 of 2. And we saw yesterday that logarithm with basis a of a is always equal to 1. So we have x, so this is equal to 1. So we have x times 1, which is x. Now consider the second hand side, logarithm with basis 2 of what? Of 1 over 8. Yesterday, we did exercises in which we had, for example, c equal to the expression, this expression, and I asked, compute, if you can, c. That is, and c was this logarithm. Okay, are we able to simplify this by applying the property of the logarithm? Well, maybe yes, because the trick is the following. How can you write 1 over 8? Can you write in particular 1 over 8 as a power of 2? Yes, you can. You can write it as 2 to the minus 3. Okay, so 1 over 8 can be written as 2 to the minus 3. Or if you want, we can do as we did yesterday. Logarithm with basis 2 of 1 over 2 to the power 3 in the first step. Then in the second, logarithm with basis 2 of 2 to the minus 3. So remember, this first hand side is equal to x, and I wrote already it here. Then look at the second hand side. The minus 3 is the exponent of the argument. You can write it in front of the logarithm. So you get minus 3 times, well, logarithm with basis 2 of 2, which is still equal to 1. So the result is simply logarithm of x, equal to minus 3. So you see, we got the same result. However, while the first approach requires to pay a little bit of attention and is not always, you cannot always apply it. Here you can apply it if you are able to transform both the first and the second side into a power with the same basis. So you can apply. If you are able to do so, you can apply the first approach. Otherwise, the second approach is more general and you can always use it. So look at the exercise. Suppose you want to solve this equation. 3 to the power 2x plus 1 equal to 1. Guys, may I tell you, there are again two approaches, only to talk. The most important is this, the one I wrote, because I told you is the more general. So if you're not very elastic and flexible with mathematics, it is convenient to use the more general. Otherwise, look, there is a possible approach here. Guys, are you able to express 1 as a power with basis 3, 2x plus 1? If you need to write in a sheet of paper, you can take it. I go slowly. Are you able to express 1 as a power with basis 3? Well, every basis to the power 0 is equal to 1. So 3 to the power 0. So you see, we can apply again the approach we applied here. The equivalent approach. Because guys, in this case, you see, we have two powers that must be equal with the same basis. So since the bases are equal, this equation in order for this equation to be fulfilled, you need to equate the exponent. So the equation is equivalent to 2x plus 1 equal to 0. I go above, which implies x equal to minus 1 over 2. But as I told you, this is required only that you pay attention, and maybe sometimes you are not so flexible. And as I told you, suppose here you had equal to 2. Well, then this approach cannot be applied. Okay, the approach I applied now cannot be applied if here instead of having 2, you had 1, you had 2, for example. However, the next approach, which is the one I wrote, can be always applied. Remember, so we are going to see a second approach as we did above. Which is your goal? You want to find x, but you see that x is in the exponent of 3. So you want to make x to fall down. How can you do it? The trick, apply the logarithm to both sides of this equality. But which logarithm is convenient to apply? Since here we have basis 3, it is convenient to take the logarithm with basis 3 of both sides. So this equation is equivalent to the one I wrote below. Now remember, the exponent of the argument of the logarithm can be written in front of the logarithm to multiply it. So you have 2x plus 1 times the logarithm with basis 3 of 3. Notice that I put inside parentheses because all the exponent multiplies the logarithm, so you have to put it inside parentheses. And you see, since I applied the logarithm with basis 3, which was equal to the basis of the exponential, we have another advantage now because logarithm with basis 3 of 3 is equal to 1, because logarithm with basis a of a is always equal to 1. Which is logarithm with basis 3 of 1? Remember, we saw it also yesterday. If you don't remember, guys, logarithm with basis a of 1 is always equal to 0. Why? We explained it yesterday. Every time you have logarithm, sorry, no, qui parte da solo, sorry, don't cancel, sometimes, I want to cancel. Okay, so I was saying, every time your logarithm with a given basis of 1, you have 0. Why? Because remember, which is the definition of the logarithm? Only to review. Is the exponent, you have to give to the basis 3 to get 1. Apply the definition. Is the exponent, if you don't remember, you have to give to the basis to get 1. Which is the exponent you have to give to the basis 3 to get 1? Is 0. So this is the reason why logarithm with any basis of 1 is always equal to 0. So you don't have to repeat this step, which was correct, but you don't have to do it unless you forget. Logarithm with basis a of 1 is 0. So we got 2x plus 1 equal to 0, which was exactly the equation we got by following another procedure above. So x is equal to minus 1 over 2. Okay, guys? Suppose, guys, you have now an inequality like this. This is an exponential inequality. You see, you have 1 over 5 to the power x smaller or equal than 9. Well, the principle, at least at the beginning, is the same. For example, guys, here I propose to approach. First approach. Oh no, I wrote it here. I wrote it here, guys. First approach. Typically, it may be convenient when you solve an inequality and you have an inequality and you have typically when you have to solve an exponential inequality and the basis of the exponential function you have, which is this one, is a number between 0 and 1, typically for students, it is convenient to rewrite this exponential function as an exponential function with basis bigger than 1. Remember, we saw yesterday that we have two different cases. The case in which the basis is the number between 0 and 1, not included, and the case in which the basis is bigger than 1. So it is convenient. This is what I did in the first way. So you see, I wrote basis bigger than 1. I transformed it. Guys, remember, how can you put 5 as a basis? Well, if you put 5 as a basis, you have to change the sign of x. So, okay, so in other terms, if you put a minus in the exponent, you have to take the reciprocal of this number. So you get 5 to the minus x, which is smaller or equal than 9. Guys, here we are in exactly a case in which we are forced to use the general procedure, that is the one that works always. How you want to make x to fall down? How can you make x to fall down? You have to take the logarithm. Which is the logarithm? Which is the basis of the logarithm more convenient to use? Is basis 5, because this is the basis of your exponential function. So take the logarithm with basis 5 of both sides. So you see, I wrote it here. So the inequality does not change. Now apply the property of logarithms. Minus x is the exponent of y. So now you can copy it. You make it to fall down. So you copy it in front of the logarithm and you cancel it from the exponent of 5. So we have minus x logarithm with basis 5 of 5. Okay. Which is smaller or equal to what? Logarithm with basis 5 of 9. Now, the first hand side, logarithm with basis 5 of 5 is 1. So you can write minus x. Minus x smaller or equal to logarithm with basis 5 of 9. Okay? You cannot reduce further this logarithm. Only an observation for someone who wants to tell it. I mean, the only thing you can do if you want is to write, but I didn't do it because it was not necessary. You can write it as 3 to the power 2. So if you want really to change this a little bit, you can write logarithm with basis 5 of 9, which is equal to logarithm with basis 5 of 3 to the power 2, which is equal to 2 logarithm with basis 5 of 3. But if you write in this way, or if you write 2 logarithm with basis 5 of 3, it makes essentially no difference because you are not able to reduce further this logarithm. You are not able to compute with your hands this logarithm. You have to use to keep it in this way. With the calculator, it's possible to compute approximately the value, but you don't have to do it. Preserve it in this way because in mathematics is, if you can reduce it perfectly, okay. Otherwise, keep it in this way. We are not able to reduce it perfectly. It's not possible. Okay, so keep it in this way. Now, we need to solve this equality. We have almost solved this inequality. We need to find x. So, I'm sorry. We need to have x in the first-hand side, so you have to change the sign. But remember, if you change the sign, you have to change it to both sides, and the verse of the inequality is changed. So you see x greater or equal than minus logarithm with basis 5 of 9. And you can stop here if you want. This is the solution. Here, again, to make more practice, I wrote equal. Equal does mean, why I wrote an equal? Because I wrote x is greater than this term, but this term can also be written as this one. So this means that x is also greater than this one, okay? So you cannot write this and then greater or equal, because this term and this one are the same, because I wanted also to show you how can you rewrite this one. How can you rewrite this if you want, but you can stop here, okay? This was already enough, but if you want, remember, -1, the minus, is like having here -1 logarithm of something. But -1, again, do the reverse step we did until now. -1 can be taken, the constant, the term that multiplies the logarithm, can be put as an exponent of the argument. So -1. So if you want 9 to the -1, and again, you can stop here. But if you want only to play with the properties, go on and you can write logarithm with basis 5 of 1 over 9. Okay, one can write it in several ways. However, this was enough. Okay, so at the end of the story, you can write as a solution x greater than this one, or x greater or equal, greater or equal, because we have this at the beginning. Okay, you remember? We have this, okay, here. Or this one. You can use the number you prefer. And so I'm writing in compact form. I wrote x belonging, the solution is x belonging to the closed interval with the extreme logarithm with basis 5 of 1 over 9. I repeat, you can write here this number, or the logarithm written in this way, or written in this way, or written in this way, or even as -2 logarithm with basis 5 of 3. There are several ways to write the same thing. Plus infinite, and then here you have to use instead this parenthesis. Remember, here you use a regular square bracket because this value satisfies the inequality. Why? Because we have the sign of equality also here. Now, I show you the second method. The second method, which is most hated by students. The second method is the following. Guys, you see here, I suggested you to transform this as a function with the basis greater than 1. And here I did this step automatically because I wanted to avoid the problem, but then I will explain this step. Now go back, go below. Now, second way, I work with my original, I want to work directly with this inequality, which is the original, okay? So I don't want to change the basis. In this case, the basis, as you can see, is 1 over 5, which is a number between 0 and 1. So, which is the suggestion, guys? You want x to fall down. As always, which is the logarithm, which is the basis convenient for the logarithm? Logarithm with basis 1 over 5. So take the logarithm with basis 1 over 5 of both sides. And what you see? Look what I did. You see, I reverted the sign of the equality. Why? Look, when applied, well, may I go on? I explain why I reverted. Why? Here, when I took the logarithm with basis bigger than 1 of both sides, I maintained the original sign. And here I took the logarithm of both sides, but with basis between 0 and 1, and I reversed the sign of the inequality. Why? This is linked to the kind of operation I performed. In particular, if you go back, we look together again. No, it's not here, it's here. The graph of the logarithm with different bases. Okay, in the first case, oh no, it's above. Okay, these are also good. Yes, this is the logarithm with basis. Let me increase, I show you better. Suppose that, I show you, okay? I want to, suppose here you have x1 and here you have x2, okay? You see, guys, x2 is greater than x1, okay? And which is the logarithm of x2, guys? Logarithm with basis a of x2. We are in the case in which a is bigger than 1, okay? A bigger than 1. Take the logarithm of x2. Which is the logarithm of x2, guys? Is this vertical distance. Here, this vertical distance is the logarithm of x2. Which is the logarithm of x1? Is this vertical distance. So you see, if x2 is greater than x1, then logarithm with basis a of x2 is greater than logarithm with basis a. Let me write x2. I go below again of logarithm with basis a of x1. So what I'm saying, if you have two numbers or two quantities and you take the logarithmic transform of both sides with basis bigger than 1, the verse of the inequality does not change because x2, look, x2 is the horizontal straight line, is bigger than x1, which is this horizontal segment. And then you observe that also logarithm of x2, which is this vertical distance, is bigger than logarithm of x1. So if you take the logarithm, therefore, of both sides with basis a bigger than 1, the verse of the inequality remains unchanged. Now, let me cancel, and I show you what happens in the second case by using again the picture. Now, let me take, okay, suppose you have x1 here and x2 here. So you see that x2 is greater than x1. x2 again is greater than x1. Now, which is the logarithm of with basis a of x2? Logarithm with basis a of x2, you have to go down, 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 is this vertical distance, which is negative. You see, this vertical distance is the logarithm with basis a of x2. Which is the logarithm with basis a of x1? Is this vertical distance, which is positive. And so obviously, this logarithm is bigger than this one. So logarithm with basis a of x2, which is this distance, is smaller than logarithm with basis a of x1. So you see that if you take the logarithmic transform of both sides of an inequality and the basis is a number between 0 and 1, you have to change the verse of the inequality. This is due to the fact that while the logarithmic transform with basis a greater than 1 is an increasing transformation, the logarithmic transform with basis a between 0 and 1 is a decreasing transform. Okay, here, however, is the graphical explanation. So I think now I can go back, and now you should realize why typically I told you students prefer to transform this basis into a basis bigger than 1 by taking the reciprocal, because then they have to take the logarithm with basis greater than 1 of both sides, and they change nothing. The sign is unchanged, okay? Because we are in case A that I've just shown you graphically. On the contrary, if you want to work with the basis smaller than 1, you can do it. Take the logarithm with basis with this basis, but then remember that in this case you have to change the sign, the verse of the inequality. Okay. Now, by solving it, guys, you can put down again x, logarithm with basis 1 over 5 of 1 over 5 is 1, greater or equal, or logarithm with basis 1 over 5 of 9. Okay, now you can keep, guys, you can keep the result here and here, because it's correct if you write it in this way. X greater or equal than this number is still okay. Here I simply told you, remember that we showed in an exercise, and this is the exercise I gave you for home, that logarithm, but you don't have to remember this property, please, guys, that logarithm with basis 1 over a of 1 over b is equal to logarithm with basis a of b. So take the reciprocal of this one is 5, take the reciprocal of this one is 1 over 9. So you see that we got exactly x greater or equal than this number, which was exactly the previous solution. But I repeat, in an exercise, it's super good if you stop here. You do not have to remember this property. No, this is not an important property. Okay. Yesterday I gave you for home an exercise to show some property, but are properties that are not necessary to be remembered. Okay, because the solution written in this way was already enough. Okay. Okay, guys. Now we're going to look at some logarithmic equation, okay, and inequalities, but a few examples. Suppose you have this equation to solve, guys. ln square of x plus ln of x. Guys, please. ln square of x is different from ln of x square. In particular, ln square of x means that all the logarithm is inside parentheses, and you cannot write 2 logarithm of x. This is different, okay? ln square of x means that is equivalent to say that all the logarithm is raised to the power 2, and the 2, and I see this error done continuously by students, even if I tell it so many times, the logarithm of x to the power 2 is not equal to 2 times the logarithm of x. Is logarithm of x square that is equal to 2 ln of x under some, okay, I don't want to go to go in detail, but what I want to tell you is that the 2 of the argument falls in front of the logarithm. Okay? Okay, guys. Yes, in reality, but I stopped for some student who said, oh, the professor told that ln of x squared is equal to 2 ln x. He made a mistake. No, I wanted to avoid to go into many details for the moment. Okay. Maybe at the end. I explain this at the end. Okay, I will explain this at the end also. But the property is that the exponent of the argument falls in front of the logarithm. But if you have all the logarithm raised to something, that something remains there. Okay, here. Oh, let me, so try to solve this inequality. Sorry, this equation, guys. We have a trick. Guys, it is convenient. You see that you see what do these two terms share in common? They have logarithm of x. So you can collect logarithm of x between these two terms, and you can rewrite this equation in this way. Logarithm of x times, if you collect the logarithm of x, you have logarithm of x plus, since you collected logarithm of x, you have plus 1. Okay, if you don't remember, do the product. ln of x times ln of x gives ln square of x. ln of x times 1 gives plus ln of x. So this equation, the second one, is equivalent to the first one. We have already applied this rule without using logarithm, because here you have a product. So we have an equation, and this equation, the first-hand side is a product equal to 0. A product, remember, very important, is equal to 0 either if the first factor is null or if the second factor is null. So for this reason, you can split this equation into two distinct equations. One, ln of x equal to 0, and the other one, ln of x plus 1 equal to 0. Okay. How can you solve this equation? Well, when you solve an equation, you want to get x equal to something, but x in this case is the argument of the logarithm. How can we transform this expression in order to get x equal? Well, we have to apply a property that I wrote yesterday. If you remember, guys, yesterday I told you, write, guys, this property, a, that comes, and I show the property, and I prove it. Logarithm with basis a of b is equal to a to the power logarithm with basis a of b is equal to b. We have shown it yesterday. So the trick is the following. When you have logarithm of a variable and you want to solve an inequality, the trick is the following. Apply the exponential transform of both sides. Before, when we had exponentials, equation and inequalities, we apply the logarithmic transform of both sides. In this case, when you have a logarithm, to isolate x, to get x equal to something, you have to apply the exponential transform. And again, which exponential transform you have to apply? Well, which is the basis of this logarithm, guys? This is logarithm of n, natural logarithm, the logarithm with basis e. So since the basis is e, you need to talk the exponential transform of both sides with basis e. So you can write e to the power n of x equal to, since we take the exponential transform with basis e of the first hand side, you have to take the exponential transform with basis e of the second hand side, so e to the power 0. But guys, look, a to the power logarithm with basis a of b is b. Here, e to the power ln means logarithm with basis e of x will be equal to x, the argument. E to the power 0 is 1. So you see, we solve it easily. Guys, may I tell you another way only to talk? Because maybe some students, oh, I don't like it. Well, if you can reason in another way, apply the definition of logarithm. ln of x is equal to 0. So 0 is the logarithm. Which is the definition of the logarithm? The logarithm is the exponent I have to give to who? To the basis. Which is the basis of the logarithm here? E. So 0 is the exponent I have to give to e to get what? The argument of the logarithm. So I got e to the power 0 equal to x, but e to the power 0 is equal to 1. So we got that x is equal to 1. Okay, it's equivalent, guys. Look at the second equality. Set it equal to 0. I mean, set this term equal to 0. What you have to do? First, put the 1 in the second hand side and change the sign. Then again, we can solve it in two ways, as we did above. So I explain again both ways. You want to isolate x, but here x is in the argument of the logarithm. How can you make x? How can you isolate x? Well, you can take the exponential transform of both sides, which is the basis of the logarithm, is e. So take the exponential transform with basis e of both sides. But e to the power ln of x, again, by applying this property, is x equal to e to the power e to the minus 1, which can be written also as 1 over e, if you want. Alternatively, how can you proceed? You are here. Alternatively, minus 1 is the logarithm. By definition, the logarithm, that is minus 1, is the exponent I have to give to the basis, which is the basis of the logarithm, e. So minus 1 is the basis, minus 1 is the exponent I have to give to the basis to get x, you see. Same. So here I did all the steps. Here instead applied simply the definition of logarithm. So we got, how many solutions we got, guys? We got two solutions, x equal to 1 and x equal to 1 over e. Question, guys. Are these solutions acceptable? Well, we have to pay attention, guys, because this for exponential inequalities and inequalities, you do not have problem because the exponential functions are defined everywhere. On the contrary, the logarithmic functions are defined only for their argument positive. For example, ln square of x is defined when x, the argument, is positive. Ln of x, again, is defined when its argument is positive. So in this case, it is better if you write also the domain. Domain is x belongs to, no, belongs x greater than 0. So you see that x equal to 1 is greater than 0. E to the minus 1 is equal to 1 over e. 1 is positive, e is positive. So also these solutions are acceptable. So both solutions are acceptable because they are both strictly positive. They satisfy the domain of the function, okay, of the logarithmic function. Vedete quanti ne abbiamo ancora? Okay, we have these two. Now, suppose you need to solve this equality. You have natural logarithm, again, logarithm with basis e of ex, e to the power x, plus e. So this is the argument of the logarithm equal to 2. Well, again, what do we need to find? We need to find x at the end. We have a problem because more than one problem. Well, first of all, the x is inside the argument. So first of all, we want to isolate the argument. How can we do? Exponential transform of both sides, which is the basis you have to take to make the logarithm to disappear, guys. Here you have logarithm with basis e. Again, take the exponential transformation with basis e of both sides. So you see e to the power logarithm of the first hand side equal to e to the power the logarithm of the second hand side. Then, which is e to the power ln of something is equal to that something. So is equal to e to the power x plus e. The second hand side is this one, remain as it is. So guys, which is our goal? So we are here. Which is our goal? We want to find x. What should we do? Well, first we have an additional a constant here, okay? So you can put the constant in the second hand side. So you have e to the power x equal to e squared minus e. Again, the original, guys, reason with me. The original equation was a logarithmic equation, okay? Then, by doing this transformation, we deleted the logarithm, and now we got which kind of equation is this one? It's the equation of the first kind we studied today. Is an exponential equation because you have e to the power x. Now, what you want to do? You want to make x to fall down because at the end of the story, we want to get x equal to something, okay? So how can you make x to fall down? Remember, now you have to apply the logarithmic transform of both sides. Which logarithm, guys? Logarithm with basis e. So take ln of both sides. You see? Now, x is the exponent of e, of the argument. So you can take x in front of the logarithm. So you get x ln of e. Look at the second hand side. Okay, I kept the second hand side as it was. Okay. One can have, okay. Now, guys, which is ln of e? Ln of e, remember, guys, means logarithm with basis e of e. Logarithm with basis a of a is 1. So ln of a is 1. So you got that x is equal to this logarithm. And one can stop here. This is a solution. Is the solution acceptable? Yes. Why? Which is the domain of this logarithm, guys? Reason with me. Which is the domain? You need to require what? That the argument is strictly positive, remember, but the exponential function is strictly positive. e is a positive number, an exponential function is always positive for every x, plus a positive number, obviously this is strictly positive. So the domain in this case of this function is all R, okay, is x belonging to R. So we have really no problem in this case, x belongs to R. Only to play, guys, only to play. This is a solution. One should stop here, okay? You don't need to go on, but you can write, and we do it, the solution in different ways, only to play a little bit with properties again of logarithm. In fact, guys, you see that you can decompose the argument of the logarithm, because you see, you have e squared minus e. Can you collect something? Yes, you can collect e. So you can write ln parentheses, collect e, so you have e times another parenthesis, e minus 1. And now, guys, what you have? The logarithm of a product. Question, is e positive? Yes, because it's 2.71, etc., etc. Is e to the minus 1 positive? Yes. So since it's positive, you can apply the property we saw yesterday. It was property B, no, it was the first property. The logarithm of a product, if B1 and B2 are positive, can be written as the sum of the logarithm. So we can write as the logarithm of B1, which is in this case ln of E, plus logarithm of B2, which is ln of E minus 1. Can we stop here or can we do something more? We can do another things now, because ln of E is logarithm with basis E of E. And again, using the properties of the logarithm, this is equal to 1. So if you write the solution in this way or in this way, the solution is correct, okay? Now, guys, we do a couple of inequality. If you have to ask something, guys, you can turn on your microphone. I know that maybe you are scared of your friends. Don't be scared of me. As I told you, I think you have to be scared of me only during the exam of econometrics if you try to cheat, but only this is the moment in which you have to be scared of me. Otherwise, no problem. If you want, you can ask even a stupid question. Don't be afraid of me, okay? Okay. If you have, and if you have question, turn on your microphone, because otherwise I have trouble to see. Oh, what's going on here? No. What's going on? Oh, devo aver cliccato qualcosa. No. Okay. Now we are going to see now a simple inequality. I mean, you don't need to be a monster in solving these inequalities. However, sometimes in an exam of Professor DH, in an exercise, you may have to solve a simple logarithmic equality or logarithmic inequality. So it's better that it's good if you know how to solve them, because these are basic concepts and professor will not explain it, okay? Will not explain these things. However, maybe you will solve an exercise, if you will do an exercise, but he will not explain everything from the beginning, okay? So these are important things that you must know before the beginning of the course. So logarithm with basis 10 of x minus 3 greater than 1. This is an inequality. We want to solve this inequality. As I suggested here, guys, it's important to pay attention to the domain of the logarithm, because remember, the logarithm, independently by the basis, is well defined if and only if its argument is strictly positive. So we need to require that x minus 3 is greater than 0. So x greater than 3. So this is the domain, or you can write it in this way or in the way you like more. So this is the domain. Keep this in mind. Now, we solve this inequality. Which is the problem? At the end of the story, you want to get x greater or equal x greater than something or x smaller than something. But x is in the argument. Which is the operation we need to perform in order to isolate the argument? And in other terms, to eliminate the logarithm on the first hand side. You need to take the exponential transform with basis 10. So take the exponential transform with basis 10 of both sides. Okay, when you take the exponential transform of basis 10 of both sides, guys, and you have an inequality, you have to pay attention. The base of the inequality is not changed. Why? Because if you remember, the same way of reasoning, I followed to explain the logarithmic transform with basis bigger than 1 or between 0 and 1 also applies for the exponential transform. So if you apply the exponential transform and the basis is bigger than 1, then the verse of inequality is unchanged because the exponential function, if you look at them with basis bigger than 1, is something like this. It passes, I'll show. No, okay, let me see. I explain again. I go above. I will not repeat all the steps because I think you must know. Again, in this case, suppose here you have x1 and here you have x2. Guys, this is the graph of the exponential function with basis greater than 1. You see that if x2 is greater than x1, like in this case, then the exponential of x2 is this vertical distance, and the exponential of x1 is this vertical distance. So you see that if x2 is greater than x1, exponential of x2 is greater than exponential of x1. Consider instead x1 here, the other case, when the basis of the exponential is a number between 0 and 1. Consider again these two numbers, x1 and x2. As you can see, x2 here is greater than x1, okay? But the exponential of x2 is this vertical distance. The exponential of x1 is this vertical distance. So whenever x2 is greater than x1, the exponential of x2 is smaller than x1. So in other terms, when you have inequalities, exponential inequalities, you have to make when you apply, not exponential, when you apply the exponential transform in an inequality, you have to pay attention, because if the basis you consider is bigger than 1, you have no problem. You don't have to change. You have to change nothing. On the contrary, if the basis of the transformation of the exponential transformation is smaller than 1, that is between 0 and 1, then remember that you need to revert the sign of the inequality. So that being said, here I took the exponential transform with basis 10, which is greater than 1, so I do not have to change the inequality, okay? But remember, a raised to the logarithm with basis a of b is equal to b, so b is the argument, so in this case it's x minus 3. 10 to the power 1 is 10, so put these 3 here, and we got x greater than 13, so strictly greater, because you see it's a strict inequality. So is this condition consistent with the domain? Yes, so we have no problem at all. The solution can be written either in this way, or if you want, as x belonging to, use a reverse square bracket, because 13 does not belong to the solution, plus infinite, use the reverse bracket, or as you know, you can use also parentheses like this, here and here. Okay, now look another inequality. Logarithm with basis 1 over 2 of 3x minus 5 greater than 2. Now, again, you want to get at the end x smaller or equal, smaller or greater, not equal, because you don't have the equality of something. However, x is in the argument of the logarithm. We want to isolate the argument and to make also the logarithm to disappear. What is convenient to do? Again, exponential transformation with basis 1 over 2. So I take the exponential transformation of both sides, you see, with basis 1 over 2. But again, you see that the exponential transform has a basis, in this case, 1 over 2. 1 over 2 is smaller than 1. And remember, if x2, suppose that this is x2, is greater than x1, then 1 over 2 to the power x2 is smaller than 1 over 2 to the power x1. Okay? The thing that I just explained. So you have to revert the sign of the equality. But, oh, sorry, guys, a typo here. Guys, oh, hey, here is Not in the solution is correct, but here is logarithm with basis 1 over 2, okay? You see 1 over 2, okay, it was 1 over 2, so 1 over 2. So a to the power logarithm with basis a of the argument is equal to the argument. 1 over 2 to the power 2 is 1 over 4. Then solve this. Oh, I didn't do the domain, but I will do it. Solve it. So put in the second hand side, do the common denominator, you make the computation, divide by 3, and you get x smaller than 7 over 4. Okay, is this a solution? We need to check, because guys, I forgot to tell you to make the domain, because this is a logarithmic function, and remember that the logarithm, the argument of the logarithm, not the logarithm, the argument of the logarithm must be strictly positive. The argument is 3x minus 5. Set 3x minus 5 greater than 0, and what you get is x greater than 5 over 3. So you have to pay attention, because without making the domain, in this case, you would have committed a mistake. Why? Because x must be smaller than 7 over 4, but at the same time, it must be greater than 5 over 3. So, in other terms, smaller than 7 over 4, greater than 5 over 3. So, you have to do what? Which of the two is the biggest number? Guys, how can you establish which of the two is the biggest number? Because let me do something. No, first, I want to see which of the two number 5 over 3 and 7 over 4 is the biggest, because this is important, guys. How can you establish it without calculator? You can make the common denominator. The common denominator is 12. So 5 over 12 divided by 3 is 4. 4 times 5 is 20. The other is 12. 12 divided by 4 is 3. 3 times 7 is 21. So we find, you see, 21 over 12 is bigger than 20 over 12. So 7 over 4 is smaller than 5 over 3. Remember, the solution is x smaller than 7 over 4. So everything on the left of x over 4, of 7 over 4 in principle. But at the same time, the domain requires that x must be greater than 5 over 3. So put these two conditions, x greater than 5 over 3 and x smaller than 7 over 4. When these conditions are both satisfied, in the interval between 5 over 3 and 7 over 4. So the solution is this one. So you see that when you have logarithm, you have equation or inequalities, it is always very important that at the beginning you pay attention to the domain, because you see, if you forget to write the domain, sometimes you can be lucky, like in the previous one. In the previous one, we had no problem at all, because the domain was x greater than 3 and the solution was x greater than 13. So the solution was fully consistent with the domain. In this case, instead, the solution was not a die, because I clicked to go close. The solution in this case, instead, if you consider the solution, you would have committed a mistake if you avoided to consider the domain. So you have to consider the domain, okay? And so this is the solution. Oh, okay, guys. Okay. Let me do the last topic, and then we do a break. Or maybe I don't know if we do completely the last topic before the break. So go back to function of one real variable. You can skip inverse function. So I tell you, I want to do only something with you. Skip inverse function. And please, I want to do this exercise with you. Skip. I mean, if you want to read everything is okay, because this, with exception with exception of equation log, line and parabola, power and logarithm, these files, the other files are files that I use as a part of a course I have in the Bachelor of Mathematics. So the course, I obviously have 90 hours for the course. I do much more things that here instead is only a crash course. So I avoid some topic, okay? I do only really the most important things that I believe are important for you in order to have all the basic elements you need to be able to attend from the beginning the lecture of Professor DH, because Professor DH will explain new things. So there is only one thing, I want to show you an exercise, and then we will do the break. But probably I will spend 15 minutes to do. Yes, do you have something to ask? You can turn on your microphone, because I don't know if no, you are not asking something. So no, I don't think so. Because they have this color, probably there are other messages on other rooms, probably. So for this reason, I see this color. So I want to show you something about symmetries and shift for very elementary function, okay? So let y equal to f of x, a given elementary function. That is one of the functions you should be able to plot almost immediately, like y equal to x to the power 2, y equal to x to the power 3, y equal to x to the power 4, square root of x, cubic root of x, root of order 5 of x, 1 over x, 1 over x squared, 1 over x to the power 3. The basic function we studied yesterday, or exponential of x, 2 to the power x, logarithm with basis 1 over 2 of x. These are the elementary functions that we saw. Okay, we did several examples, okay? We consider different kind of function, and in particular we saw very elementary function. And this graph must be done immediately without performing a complete study of the graph of the function with all the mathematical steps that we still have to see. Okay, suppose you have a graph of an elementary function, and I want to show that if you know already how to plot f of x, you can plot other function like the graph of the function of f of minus x, the graph of the function y equal to minus f of minus x, the graph of the function y equal to minus f of x, the graph of the function y equal to f of absolute value of x, y equal to absolute value of f of x, and y equal to absolute value of f of absolute value of x. Because taking into account of symmetries and shifts, you are able, from the simple knowledge of f of x, to derive all this, to plot the graph of this function without the need of doing other graph. In particular, I'll explain it with a particular function. Okay, here I reported other case. We'll discuss them, all of them. I will show all of them. For example, suppose that your basic function is y logarithm of x. And now I want you to plot, starting from the graph of the logarithm of x, that is an elementary function, and you must know immediately its graph. Okay, not today, if you don't remember, but for the course of Robert, in the course of mathematical method and tools, you must know immediately which is the graph of the logarithm with basis bigger than 1, and which is the one with basis smaller than 1, okay, between 0 and 1. Suppose you have now y equal to logarithm f of x, and I ask you, plot all these functions where f of x is the logarithm of x. Okay, we start from the first case, f of minus x. So reason with me, y is equal to ln of x, which will be the function f of minus x, will be ln of minus x. So the graph we want to plot now is the graph of f of minus x. Wait, there is an helicopter. Guys, which is the relationship? Remember that we studied when a function is even. Remember that a function is even when f of x is equal to f of minus x. So, which is, guys, the relationship between the graph of f of x and the graph of a function f of minus x? The graph of f of minus x is the symmetric of the graph of f of x with respect to the vertical axis. Why? Because, for example, f of minus 1 is equal to f of 1. F of 2 is equal to f of minus 2. So the graph of f of minus x is the symmetric with respect to the vertical axis of the one of f of x. So instead of performing a complete study of y equal to logarithm of minus x, we can simply use symmetries, which is the graph of ln of x. You must know it very well because we plotted it yesterday. We explained it is the graph of the logarithm with basis e. And you know that the graph of the logarithm is something like this when the basis is bigger than 1. And it passes to the point 0, 1. And I do it with a non-continuous black line. But I wanted to plot here the graph of f of minus x, which is ln of minus x. Well, as I told you, the relationship is between f of x and f of minus x is the relationship between the graph of a function and it's symmetric with respect to the vertical axis. So here, in fact, you see it passes through 0, 1. Here it will pass it from 0, minus 1. At 2, this function passes through ln of 2. At minus 2, this function passes to ln of 2. So you can plot this one, which is exactly, okay, I did it poorly because I did it with my hand. Obviously, it's not clearly very symmetric, but I tried to do, but essentially, this should be perfectly symmetric with respect to this one. But obviously I did it with my hand, so not so precise. Okay, now go on. I asked, plot the graph of minus f of minus x. Guys, ln of x is this one. F of minus x is ln of minus x, minus f of minus x is minus this one. Guys, we did it so many times, but here is in a different context. Which is the relation? I mean, we saw that a function is symmetric with respect to the origin if and only if minus f of minus x is equal to f of x. So in other terms, what do we expect? The graph of of minus f of minus x is the symmetric with respect to the origin of the graph of f of x. So we try to do it now. You see, I wrote everything. So here I plotted my original graph. Okay, so when this function, this is a graph of ln of x, when this function goes below, you see it tends to become more and more negative. We say that the function tends to minus infinite. The other, the one we plot, which is this one, since it must be symmetric with respect to the origin, it must tend on this direction to plus infinite. We say that is the value of x, of f of x becomes bigger, bigger, and bigger. Then guys, wait a moment, I close the window because they are talking. Yes, I am back. Yes, here you see, guys, that as we move in this direction, the logarithm becomes bigger and bigger and bigger and bigger. So as we move in this direction, the logarithm becomes smaller and smaller and smaller. So the graph of this function is the symmetric with respect to this one from the perspective of the origin. I will show then another way to plot it in a moment, which is even simpler, because maybe this one can create confusion, this way to proceed. But first, I introduce case C, which is the relationship between f of x and minus f of x. So we need to plot the graph of minus logarithm of x. Well, look with me. First, in black, I plotted with a non-continuous line the graph of logarithm of x. Which is the relationship between logarithm of x and minus logarithm of x? Well, for the same value of x, when logarithm assume, for example, the value, suppose that here is 2. Here you have the value ln of 2. Minus f of x will assume the value minus ln of 2. If suppose that here is 3, you have 3 here, go above, the vertical distance is ln of 3. Minus f of x will assume minus ln of 3. So, in other terms, the relationship between f of x and minus f of x is the following. The graph of minus f of x is the symmetric of f of x with respect to the horizontal axis. And so I can plot it. Before going on, guys, I want for a moment to come back. Remember, there is another simpler way to plot. I suggest to avoid to plot minus f of minus x directly, unless you're very good, or because otherwise you risk to create confusion. I explain a simpler way to do it. We can do step by step, because minus f of x, remember, I want to plot at the end of the story minus f of minus x. But, so, we can proceed by step. First plot f of x. Then, which is f of minus x? As I told you before, f of minus x is the symmetric of f of x with respect to the vertical axis. So is the branch we plotted above. So it's this branch. So plot this branch, let me see with another color. Maybe I hope. Okay, let me do it. I do it poorly, guys, because I have troubles in doing it, but with my finger. Yes, I did it poorly, but guys, I did it very poorly because I don't see. Okay, because I use the finger, so I'm not able to see. So this should pass here, and should be symmetric with respect to this one. And the green is f of minus x, but you want to plot minus f of minus x, which is the relationship between f of minus x, which is the green one, and minus f of minus x. Minus f of minus x, which is the red one, is the symmetric with respect to the horizontal axis of f of minus x. So take the symmetric of this one. I mean, I did it poorly, but it is this one, okay? It's the one I plotted in red. So instead of doing everything in one step as I did in point B, first it is convenient to take f of minus x, which is the green and which is the symmetric with respect to the origin of f of x. Then to compute the final step, consider the symmetric with respect to the horizontal axis of f of minus x, that is the symmetric of the green. And by doing so, you get the graph I did previously in one step, because it's easier by performing 2 steps. So now I want you to plot the graph of f of absolute value of x. So in this case is ln of who? Absolute value of x. Remember, apply the definition of logarithm, of absolute value. If x, guys, in principle, okay, f is greater or equal than 0, then the absolute value of x is equal to x. But to be precise, look, I wrote logarithm of x if x is only greater than 0. Why, in this case, I avoided to report the equality? Because the absolute value of 0 makes sense, which is 0, but logarithm of 0 does not make sense. So for this reason, instead of writing x greater or equal than 0, I wrote x greater than 0. And remember, if the x is negative, so if x is negative, the absolute value make it positive by multiplying it by minus 1. So logarithm of minus x. So the graph tells that logarithm of absolute value of x is equal to logarithm of x if x is greater than 0. So do it. This is the graph of logarithm of x. If x is smaller than 0, the graph is the one of logarithm of minus x. It is what we plotted in point A. this logarithm of minus x, which is the symmetric of this one. So this is the graph, putting together, this is the graph of the logarithm of absolute value of x. Absolute value of f of x. F of x is the logarithm of x. Remember, here we can go faster because yesterday we studied the graph, how to perform this kind of graph. In particular, what I told you yesterday, by applying the definition of the logarithm, of absolute value of something is a function which is always greater or equal than 0. And yesterday I suggested a trick without having to distinguish the two cases. I suggested plot first the graph of the inner function. Which is the inner function, guys? The logarithm of x. And this is what I did if you look. We're using a non-continuous black line. So this is the graph of ln of x. But please, remember, look at this graph, the one in black. Forget about the red for the moment. You see that for x greater than 1, the graph of the logarithm of x lies above the horizontal axis, so is greater or equal than 0. And since for x greater than 1, the logarithm is greater or equal than 0, see the graph is above the horizontal axis, the logarithm says, okay, I'm okay as you are, so you can color this branch. Now, for x belonging to 0 not included and 1, you see that the graph of the logarithm lies below the horizontal axis. And the logarithm says, and the absolute value says, I want to make you positive. I multiply you by minus 1. So what means minus 1? Minus ln of x. But which is minus ln of x? Is the symmetric of this branch with respect to the horizontal axis. Do it and you get this sort of reversed shark fin. I don't know, shark fin. Okay, guys. Remember, we did something similar yesterday to plot the straight line in this way. We plotted first this one. No, okay, non sto a rifare il disegno. I have to do it. We did it something like this. Yesterday we plotted this one, then we colored this, and we said, oh, here we need to take the symmetric, and this was the graph of absolute value of x that we did yesterday. If you look yesterday, we did this graph. Okay, but we did other graph yesterday, absolute value of x to the power 3, absolute value of cubic root of 3, yes, of x, sorry, so we did them yesterday. Then guys, really, I want to finish this exercise, then we do a break, okay? But it's only an exercise, it's not difficult. So guys, in this case, look, we have absolute value of f of absolute value of x. In other terms, we want to plot absolute value of ln of absolute value of x. We can apply the same trick as before, because this function, since this is the function inside the absolute value, I mean, you have a function completely inside an absolute value. So the graph of this function is greater or equal than 0. So this means that this graph will always lie above the horizontal axis. So as we did previously, I suggest to plot first the graph of the inner function. Well, we did already the graph of the inner function, guys, because it was this one. So first plot in black with non-continuous line this graph, which is the graph of the inner function. So I did this one and I did this one. And again, reason as we did in the previous point, the absolute value makes everything inside to be greater or equal to 0. So look here, look at this branch. You see that for x greater than 1, the graph of this function is already greater or equal than 0 because it lies above the horizontal axis. So color it with red. Between 0 and 1, you see that this graph lies below the horizontal axis. So the absolute value tells multiply this branch by minus 1. So if you multiply it by minus 1, this means that you have to take the symmetric of this branch with respect to the horizontal axis. Plot this one. Then between minus 1 and 0, you see that the graph of the inner function lies again below the horizontal axis. And again, the absolute value tells, oh, you are negative. I multiplied you by minus 1, and so I considered you're symmetric with respect to the horizontal axis. So do the symmetric of this one with respect to the horizontal axis, and so track. Then for x smaller or equal to -1, you see that the graph of the logarithm of absolute value of x lies above the horizontal axis. So the absolute value is happy and say, okay, I color you because I like you as you are, so color it. So you get, in this case, a sort of double reversed shark fins. I don't know. Penne, due for Italian people, due pinne di squalo rovesciate. Let me see. If you have question, guys, otherwise I do the last two examples, because I always see something here, but you are not you, I think, because I told you talk with if you have something to ask. Something to ask. Now, this graph, f of x plus 1, which is the relationship between f of x and f of x plus 1. Simply, for every given values of x, the graph of f of x plus 1 is simply shifted upward by 1 unit. So suppose that this is in blue, this in a black non-continuous line, the graph of ln of x. You know, for example, which is ln of 1. When x is equal to 1, the value of the logarithm is 0. Okay, which is the value of ln of x plus 1? Is 0 plus 1. So you see, this vertical distance is exactly equal to 1. If you take, for example, 2 here, which is the value of the logarithm? Put 2 inside the logarithm. Here you have the value logarithm of 2. I do it poorly, guys, because, you know, I have troubles. I do not have it. So it's logarithm of 2. Which is the value here, guys? So go above. When x, this is shift above by 1 unit. So since here is ln of 2, this vertical distance again is equal to 1. So this would be ln of 2 plus 1. So essentially what I'm saying is that all these vertical distance, you have to take the vertical distances, I did it poorly, but all the vertical distances, all the vertical distances, all the vertical distances must be equal to 1. So 1. If you have minus, obviously, you have that the graph is shift downward. So if you add in general to f of x a constant, is simply an additive constant, then the graph of f of x is shifted upward or downward by k units. K could be positive, so upward, or down if k is negative. Okay. The last one, and then we really do the break. F of x plus 1. So, which is the graph of, remember, ln of x, so is our basic function. So f of x plus 1 is logarithm of x plus 1. Well, when you have an additive constant, or I mean for an additive constant plus 1 or minus 1 in the argument, and in the argument you have x, this you have an horizontal shift. You have an horizontal shift. In particular, contrary to what you expect, if you have x plus 1, suppose this is the logarithm, okay, then you have a shift to the left. So your function shifts horizontally to the left of 1 unit. This means that when the logarithm is 0, for x equal to 1, ln of x plus 1 is 0 at x equal to 0. So it's shift of 1 unit to the left. In particular, guys, if you don't believe me, or if you don't understand it, think about the domain of the logarithm. Which is the domain of the logarithm? The basis, the argument must be positive. Which is the argument here? So remember, which is the, in case of the logarithm of x, which is the domain? X greater than 0. Okay. When you have x plus 1, which is the domain? X plus 1 greater than 0, which implies x greater than minus 1. In fact, you see this graph. This is the graph of ln of x, which is defined for x greater than 0. As you see, as we getting closer and closer and closer to 0 from the right, our function tends to get closer and closer and closer without reaching the vertical axis. And we had, in fact, x greater than 0. For our function here, Lx plus 1, we have that domain is x greater than minus 1. So this means, guys, since it's only a shift, that in this case, as we approximate minus 1 from the right, the function tends to become closer and closer and closer. So you see that you can understand about the type of shift by simply looking at the domain, because you see that the domain in this case is shifted to the left of 1 unit compared to the domain of ln of x. If you have ln of x minus 1, on the contrary, I do it poorly, don't do it. If you have ln of x plus 1, on the contrary, the domain, ln of x minus 1, you will have a graph like this. Here you have 2. I do it poorly, okay, guys? No, neanche funziona il dito. My finger does not write. Okay, so this green, on the contrary, is the graph of ln of x minus 1, which is the domain of ln of x minus 1. You have to require x minus 1 to be greater than 0, so x greater than 1. So as we move towards 1 from the right, our function decrease, tends to be closer and closer to this vertical line without reaching it. Okay, so these are the shift. So I think now, if you don't have question, we can stop. And since we work too much, I think I can give you 20 minutes of break today. Or would you like 15? No, if you want that 15, we do 15. If you want other guys, no, since we need to start a new topic, today we start exactly at 11, okay? So then we work then 50 minutes until 10 to 12 to 12, okay? So we work until 10 minutes to 12. So we get now 22 minutes now of rest, and then we do 50 minutes continuously, okay? Is it okay? So I take you 50 minutes later, but now I give you 22 minutes of rest. So we can continue again at 11 if for you it's okay.
Okay, thank you.
Well, thank you. Thank you, guys. You have questions? You can ask me. Do you have questions? Okay.
Oh, now, thank you.
Oh, okay, thank you. Okay, guys. If you have no question, I go also. I'll be back. If you don't have question, I'll be back later. So I turn off my mic, turn on my microphone. Okay, guys, we still wait until 11, 30 seconds maybe. Okay, guys, again, if you have trouble, stop me. If you don't see what I'm sharing, let me know. Okay, so guys, we go back to the previous file, but we finished it. Guys, now I hope you are still here. If you want to make practice, guys, even in the future, it depends on you, okay? If you go function of one real variable, this file, at the end, I prepared a lot of exercises, all with the complete solutions. So for example, I really recommend, especially if you have troubles with these things, otherwise you don't have to do exercises, but if you have troubles, here you have exercise 1 concerning the domain, determination of the domain of different function. I wrote all the function here. Verify that the following function are even or odd, so you can make practice on even and odd function. Then remembering the graph of logarithm with basis a of x, plot the graph of the following function. So by using symmetries, absolute value, etc., etc. And remembering the graph of y equal to a to the power x, plot the following function. So you can plot again by using the instrument we studied. It's like an exercise like the one we did just now. Okay, both 3 and 4. Sketch the graph of, you have absolute value of a parabola, square root of absolute value of x. You can sketch the you can do the graph intuitively of these functions. So this can be very, very, very useful. Well, you can skip 6 because I didn't review with you inverse function. Again, if you want to make practice about symmetries, etc., you can do also exercise 7. You can do also exercise 8, guys. But guys, these graphs are very useful, these exercises, to make practice if you are not very quick to plot graph of easy function. But if you do them, you learn a lot. Okay, you get practice. Plot the graph of this function, you can do it. This one, plot the graph of this function. Here you have other function and find the domain, especially if you have troubles, because this, I mean, if you are already able to do these things very well, no problem at all. You don't have even to think, review what we did together. And here, on the contrary, if you have troubles, I recommend to do more exercise, to do a lot of exercises. And here you have all the solution with all the steps, so you can really check if you did everything correctly. Okay, now I close this file and I'm going to open another one. So we are going to open the file. Let me see with you. Let me see with you guys. And okay, crash course econometric RESD. No, it's not this one. Crash course RESD, mathematics, and we did let's skip limits and continuity because it's not my goal, but go instead to the one of differentiation, which is very, very important. So I suggest to open this file. Let me open it. Let me open the file. And guys, now we start. Okay, wait a second. I close my window. Okay, guys. Obviously, guys, this is a crash course. This file, I use also this file as file A of functions, file B on limits and continuity that I avoided, but I provided it if you need it in the future. I mean, if you want to have a review, because it contains all the my explanation on an intuitive explanation and a lot of exercise. If for any reason at any moment you need to review something, you don't know where to look, and you can look here, for example. Here is a file on differentiation. Here obviously is full of details, but we go only to the information we need. In particular, we are going to talk of differentiation. I will avoid a lot of details because the most important things is that you remember which is the meaning of a derivative, the graphical meaning of the derivative. So I don't need to explain how to build the derivative, etc., with all the steps as I do in the bachelor. Otherwise, we will never finish. But I need to learn you. So you must know the meaning of derivative, the graphical interpretation. You must know how to compute derivatives. Okay, because with Professor Dieci, you will have a lot of times to compute derivatives. So derivatives are fundamental. So you must be able to compute derivatives. So here, guys, I simply tell you, if you want to read only with you this small introduction, not the introduction, but these small things, an important topic in many scientific disciplines, including economics, like you, is the study of how quantities change over the time, or how they change as an effect of the change on another variable. For example, which is the change in the price of a bond due to a given change of its yield to maturity, which is the impact of the profit of a firm of a given increment of the production costs. To answer to those questions, you need information about rate of change. And the mathematical concept used to determine rate of change is the derivative of a function. So guys, you can skip, yes, you can skip introduction. This is the construction of the derivative for the student of the bachelor. So you can skip, you can skip, you can skip, you can skip. So go on, go on. Derivative and geometric meaning, go on, go on, go on. Yes, go on, go on, go on. You can, I mean, if you like, you can read it, obviously. It's always useful, but you can avoid. Yes, you can skip. Yeah, skip for the moment. Skip this one. Yeah, stop here. So we are at page 6. I want to show only which is graphically the meaning of the derivative of a function. Then I will explain how to compute derivative. But first, I want you to give only the intuition. So I avoided to explain, to provide all the construction of the derivative starting from the limit of the incremental ratio because it's too long and you will not use it. So the idea is the following. I explained this picture, but please focalize yourself only for the moment. Suppose you don't have you have nothing here, but only this black graph, the one I'm touching. You see this black graph. I am touching it. So suppose that this is the graph of your function. So this is your system of orthogonal Cartesian axis, okay? And you have the graph of this function, the one in green, in black. Then consider a point. Suppose that you have a point. I called it x0. Okay, x0. Which is the value of the function at x0? The value of the function at x0 is f of x0. Okay, because you have simply to insert x0 inside your function. Well, the meaning of the derivative is the slope of this line, the one I'm touching. You see this line? This line is the tangent line to the graph of your function at the point x0. You see here is the point x0, go, okay? So this straight line is the tangent line to the graph of your function at the point x0. The slope of the tangent line at this point, and I denoted it with f prime of x0, is the derivative of your function evaluated at x0. So in other terms, I repeat then, but then I summarized everything. So try only to pay attention. So what I'm saying is that the derivative of a function f is denoted as f prime of x. So f of x is the function. The derivative of the function is another function called f prime of x. In particular, the derivative of a function evaluated at the point x0 is the slope of the tangent line to the graph of that function at the point x0. So is the slope of the tangent. Okay, so let me see. Okay. So this is important. Now I tell you what is important, guys. So keeping in mind what I just have shown you, this is important, this one. So we are at page 6. So we read together, as I told you, f prime of x0 is the slope of the tangent line to the graph of your function at the point x0, and I've shown it graphically. So what does it mean in practice, f prime of x0, which is the meaning of the slope? Is, guys, the instantaneous, so remember this name, instantaneous growth rate of the function at the point x equal to x0. So I repeat, what you have to remember, the tangent line, so the derivative of the function evaluated at a particular point is the slope of the tangent line at this point, and therefore it measures the instantaneous growth rate of the function at the point x equal to x0. And that is, I explained the meaning of instantaneous growth rate. That is the derivative f prime x0, which is a number because it's the slope of the tangent line to the graph of the function at x0, which is also called instantaneous growth rate. It estimates, so it's a measure of the estimate of the change in the value of y is your function, due to a change of 1 unit of x at x equal to x0. So it estimates the increment, or which can be positive or negative, so the increment in the value of the function if you increase x of 1 unit starting at the point x0. So f prime of x0 is the slope of the tangent line to the graph of f of x at x0. It is the instantaneous growth rate at x0 of your function. That is, it is an estimate of the change in the value of your function as you go from x0 to x0 plus 1. That is, as you increase x of 1 unit starting from x0. But note, this is not the true change. This is the estimate of the change of y by measuring the change, moving yourself. I will show it then in another graph, measuring this change along the tangent line and not along the true graph of your function. So let me go above a little bit. Then I go. So I repeat, this part is very important, but now I want to explain it again, and then I go back. Notice, let me show you. Suppose this you are at the point x0. F prime of x0, I told you, is the slope of the tangent line to the graph of your function. Our function is this black line, black curve. It's the slope of the tangent line at the x0 of our function. And what does represent? It represents the instantaneous growth rate. That is the estimated, I told you, and then I show you graphically, the estimated change in the value of your function as x goes from x0 to x0 plus 1. Why estimated? Look, here is x0, okay? Here is x0. Suppose that you go from x0 to x0 plus 1, which is the true change in the value of the function. You see, the true change, here you have x0 plus 1. Go above, 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 until you touch the graph of your function. You see the black one here. I'm on the black one, okay? So you see, this vertical distance, fx0 was the previous value when x was equal to x0. If the value of x becomes x0 plus 1, the value of the function is all this distance. Start from here, go below, 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 below. And it's too small, so I don't write it. But if you go horizontally, here, you go horizontally, you have f of x0 plus 1. This vertical distance, therefore, which is the difference between the new value of your function at x0 plus 1 minus the previous value, which is this blue line, blue vertical line, is the true change in your function as you change x from x0 to x0 plus 1. On the contrary, I told you that the derivative evaluated at x0, which is the instantaneous growth rate, is the estimated change in the value of f as x passes from x0 to x0 plus 1. Why estimated? Because this change is not computed along moving yourself along the real function, but this is the change estimated if you move yourself along the tangent line. So x0 is this one, x0 plus 1 is this one, so go above until you touch the tangent line. So which is the initial value of the function? F of x0, which is the value estimated for the change in the function if you move along the tangent line. You read it here, is this vertical distance from here to here. So which is the change estimated if you move yourself along the tangent? Well, you have to, the original value is this one. The new value is this one. So you have this vertical distance minus this one. So in brown, guys, you see what? You see the estimated change. So this is, guys, the length of this segment of brown segment is exactly equal to this corner, to the measure of this corner, is f prime of x0 is the slope. So the slope is the instantaneous growth rate, that is the estimate at the point x0 of the expected increment of your function f as x passes from x0 to x0 plus 1. Why is called expected or estimated increment? Because it's not the true increment. The true increment is this one, this vertical blue line. Because to find out the exact increment, you should read the increment by looking what? Looking at the change in the value of f by moving yourself along the true function. Instead, this is only estimated because we estimate this change not by looking for the new value of the function, but by looking from the value that you read directly on the tangent line of the function. So this is the instantaneous growth rate at 0. So you see that you commit a mistake. This small distance is the mistake you commit. Let me see. Yes, in a moment I'll clarify it again by introducing the definition of the notion of differential. I want to tell you something, to write it something next, so maybe you understand even better. So, guys, no, I tell you later. I continue with this explanation. Okay, so I told you this part is very important. Okay, this part. Yeah, you can skip all the other things. So look at this picture. Okay, look at the picture and only at the things that I added here. I told you the explanation and I provided the explanation also on the graph. Why? The notion of derivative is strictly linked to the notion of differential. So to clarify, this is important, the utility of the derivative at x0, we introduce the notion of differential. And so I will explain again. So the linear definition, okay, don't have to remember really the definition, however, read the definition. The linear function that associate to the increment delta x0 of length equal to h, the product between the derivative of the function at the initial point x0 times the length of the increment delta x0, which is also h, is called differential of your function relative to the point x equal to x0 and the interval, I forgot to write interval, and the interval h. So the differential of your function at the point x0 and relative to the interval h, or delta x0, is denoted in this way. d f of x0 is equal to f prime of x0, so this is the notation of differential, is equal to the derivative evaluated at x0 times delta x0. But since we called delta x0 equal to h, you can write f prime x0 equal to h. So I repeat, this is the differential of your function relative to the initial point x0, to the point x0, no, initially, point x0, and relative to the interval of length h. I try to explain graphically again the meaning of differential. I try to explain the meaning of differential, which is strictly linked to the meaning of the derivative. So again, I plotted a graph. Suppose that this black line represents the graph of your function. Consider the initial point x0. We want to evaluate the differential at x0 relative to the an interval of length h. So I fix here x0. I consider then an increment of length h. So I call delta x0 means the variation of x when the initial value is x0, and I called it h. So the new point will be x0 plus h, or if you want, x0 plus delta x0. Then, now go above vertically, which is the value of your function when x is equal to x0. You have to go above, until you touch the graph of your function, and then go horizontally, and this vertical distance is f of x0, which is the value of your function as if you increase the value of x from x0 to x0 plus h. So you have to go here, go above, until you touch the graph of your function. Then go horizontally, and you get fx0 plus h. So I'm asking you, if x passes from x0 to x0 plus h, which is the change in the value of the function? Well, the change in the value of the function is this one, is delta f of x0, okay, which can be called also delta y, I don't know, delta y0, and is given by what? If x passes from this value to this value, you see that the value of your function passes from f of x0 to f of x0 plus h. So this vertical distance is delta f of x0, or also called delta y0. So this distance, you see, delta y0. So this is given by f of x plus h minus f of x0. So this is the true change of the function in the value of the function as x passes from x0 to x0 plus h. Now, plot the tangent line to the graph of your function passing through the point x0. So this is the tangent line. Okay. The slope of the tangent line at x0, I told you, is called f prime of x0, is the derivative of the function evaluated at the point x0. This is also called... Porca puttana, ragazzi, scusate, moschito, porca vacca, bestia al moschito. Oh, sorry. So, this is called, I was saying, is the derivative evaluated at x0, so it's called also instantaneous growth rate. Now, look, which is the meaning of differential? Well, the differential is defined as f prime of x0 times h. Look, graphically, estimate now, guys, estimate now the change in the value of the function by moving yourself along the tangent line. So you have to go, the initial value is f of x0, then increase and go to x0 plus h, then go vertically until you touch the tangent line. So delta y0, guys, the differential is all this vertical distance, okay, because is the difference between the estimated new value of the function computed using the tangent line minus the initial value. So you see this distance minus this distance is this red distance. This is called dy0 or df of x0. This is the differential at the point x0 relative to the interval of length h. And what you want to realize, if you estimate the true change is delta y0, which is the black, through the differential, you see that in this particular example, you are overestimating the change. And in particular, you commit an error. Which is the error you do? The error you do is the difference between the estimated dy0 and delta 0. So the error is this vertical distance. This vertical distance is the error. And the differential is simply given by the product between f prime of x, which is the f prime of x0, which is the derivative here, and this length, which is h. The product between f prime of x0 and this length gives exactly this vertical segment. So the differential. So differential is the product between the slope. But remember, the slope is the instantaneous growth rate. Suppose that this is 1 unit. Suppose this is 1 unit. Okay, is the product between the slope and, because remember, the instantaneous growth rate is the estimated growth rate from the estimated increment, for 1 unit of increment of x, starting from x0. So in other terms, the differential is simply the instantaneous growth rate times the length of the change in x considered. I want you to observe that if you consider a smaller increment, for example, suppose that instead of h, you have h instead of being here, suppose it's here, the new increment, x0 plus h. Then you go above, and you see which is the true change in the value of the function is given by the value here minus the value here. Sorry, I did a mistake. Which is the true change? Is the value here, you read it on the function, minus this one, so minus this. Okay, is this distance, the one I'm touching. Which is the error you commit if you use the differential? Is this vertical distance. So you see that in this case, the error is much smaller compared to the previous one. What I want to say, smaller the length of the change in x0 considered, smaller the mistake you commit and better the approximation. So if you consider a small change of x0, either positive or negative, you see that essentially the graph, consider for example here, you see this green circle. So in this interval, for example, you see that the graph of the tangent and the graph of the function are almost indistinguishable. So the approximation done by using the differential is very accurate if you consider small changes from x0. If you consider instead a huge change, you see you commit a mistake. But smaller the change of x, smaller h, in other terms, smaller h, better the approximation you get by using the differential. Okay, so the product, so which is the meaning of the differential? Is the estimated change in the function as x passes from x0 to x0 plus h, and is given by the product between the instantaneous growth rate or slope of the tangent line at x0 times the length of the change in x considered. Okay, that being said, there are some quantities very important in economics. Oh, I wrote it here. So guys, this I wrote. Yes, you can. Okay, so guys, read everything I wrote below, because I was saying, guys, what I wrote, I explain now, guys, is written also below. Okay, so this is also important. Okay, also important. This is what I told you. Okay, so important is the intuition of derivative that I've shown you in the previous page, and the notion, the meaning. This page is important. Okay, then Guys, I show a couple of examples before going on. Guys, yeah, here I show a couple of examples, but not everything. Observation. Are all continuous function differentiable or derivable differentiable in all the points of their domain? The answer is no. Differentiable means that you can compute the derivative. Are all continuous function differentiable in all the points of the domain? The answer is no. If you have a function which is continuous, a continuous function is not necessarily differentiable in all the points of the domain. And now I'm showing you an example. Consider this function y equal to absolute value of x. And reason with me, don't look at the explanation, only with the reason with the graph. This is the graph of absolute value of x. We derived it yesterday. Well, this function is not differentiable everywhere. In particular, differentiable means that you can compute the derivative. It's only an anticipation. You can compute, this is a continuous function, you see, but you cannot compute the derivative here. Why? Guys, I told you, which is the meaning of the derivative at a point? Is the slope of the tangent line. Are you able to plot the tangent line to the graph of this function here? Well, we have a right tangent, which is equal to this branch itself of the graph of the function. And we have a left tangent, which is this one. So which is the slope? Well, this tangent line has this slope. The other tangent line has this smaller slope. So we cannot, it is not differentiable, guys, because to be differentiable, you must have a unique tangent. Okay, this is right, guys. This is a point like this. You cannot have one tangent, even if the function is continuous. So in a point like this, the function, we say that, okay, you can compute the derivative everywhere of this function with exception at this point, because at this point, which is the tangent? Guys, you have both a right and a left tangent. So at this point, the graph, the function is not differentiable. I want to show other cases of continuous function which are not differentiable. Suppose you have a function like this. This continues everywhere. So is this function continuous? We plotted it yesterday, guys. Well, it's not differentiable everywhere. Why? Because it is possible to show that the value, when I will show the derivative, is clear why it's not differentiable, but I can tell you already now that the tangent line to the graph of this function at the origin is vertical. And a vertical line, as I told you, I think in the first lecture, as we said that a vertical line has an infinite slope. You cannot find n equal to a real number, okay? So for this reason, at point in which the function admits a vertical tangent line, the derivative does not exist. The derivative does not exist. So the derivative does not exist if the right and the left tangents are different, like in the previous case, the point of the previous case. Oh, I get the mosquito finally. Oh, sorry. So in the previous case, it does not exist, the tangent, because you have, in theory, two tangents. So it does not exist, sorry, the derivative. Here, it does not exist at this point only because the tangent is vertical. So at point in which the tangent is vertical, a function is not differentiable. At points in which you have a right tangent and a left tangent, the function is not differentiable. Then I plot this graph. If you do the exercises for home, you have a graph like this. Typically, this occurs when you have a parabola inside an absolute value. The parabola here is negative, then you have to take the reciprocal. Typically, I repeat, when you have a parabola, which like this one, you take the absolute value, you get something like this, but this is not what I wanted to talk. Is this function, you see, this function x continues everywhere, it continues because you never have to raise your pencil. You can plot the graph without raising your pencil from the sheet of paper. Okay, so it continues. However, is differentiable everywhere? No, it's not differentiable at point A and is not differentiable at point B. Why? Because from at point A, you see you have two tangent in A and you have two tangent in B, one left tangent and the right tangent. So again, this function is not differentiable at point A and B. It means that you cannot compute the derivative. So guys, for home, you have only to look the things we have seen up to now. I mean, I told you to okay, if you want, I write also this in blue. Look at this graph, the interpretation. You can skip this based on something else, you skip it. It was a more formal explanation. This one, look at this graph and look at, okay, skip it because this is a formal proof by using the definition, but we avoided to use the formal definition as the limit of the incremental ratio, and look at this graph. Okay. So theorem, if a function is differentiable at a point x0, then it is also continuous. So if a function is differentiable at a point, for sure at that point is continuous. Obviously, think to the example I did, the opposite is not necessarily true, because I've shown you three graphs in which the function were continuous at a given point x0, but in all these points, the function was not differentiable. So the theorem is also important. Now, before starting to show the differentiation rule, maybe we'll do it in the afternoon, I think, I want to tell you something that the professor really required other years to, your professor of math asked me to explain. So the concept of growth rate, instantaneous growth rate, relative instantaneous growth rate, and elasticity of a function at the point, say at the point in x0. What is the growth rate? So now I want to explain. So we have, first of all, the growth rate. Remember, if you consider a straight line, the slope, I told you the first lecture, that is also the growth rate, because the slope of a straight line, guys, represent what? The increment of y for an increment of x, and is constant. So a straight line, the slope is m, does not change. So in other terms, guys, suppose you have a function, guys. Let me go back for a moment. Remember, go at page 6. Okay, here at page 6, I use this picture to explain the meaning of the slope of instantaneous growth rate. But consider in this picture also an increment of length h. So go here, tac, tac, x plus h. Go above, until you touch the graph of your function. Well, now plot the straight line passing through these 2 points. So this is second. Second is this one. You see, is this line, this one. This was the derivative. Okay, now we don't talk about derivative, but we talk about second. Second is the straight line passing through this point and this point. Okay, this is the second. Call the slope of the second as m. M, guys, is also the average growth, so is the slope of the second, but it's also the average growth rate. In particular, let me see if I wrote it below. I wrote it, but I want you to. So I will add it the next page. So we've add here m, guys. M is the difference between delta fx0 and delta fx0, you remember, is fx0 plus h minus f of x0, okay? Divided the length of the interval, which is x0 plus h minus x0, so divided by h. So the slope of the second, guys, the slope of the second passing through these two points is the average growth rate of the function f of x with initial point x0 and relative to the increment of length h. Because now, guys, so please write it, m is equal to delta fx0 divided by h. So m is equal to delta fx0, where delta fx0 is this increment, the increment of the y, divided the increment of the x, which is x0 plus h minus x0. So this is called average growth rate. And notice that if you multiply m by h, what you get? Delta fx0. So you can get delta, this vertical distance, I repeat, which is delta fx0, by multiplying the slope of the secant times h. So I repeat, m is the average growth rate because it has been obtained by dividing, look, the effective change in the value of the function by the length of the interval representing measuring the increment of x0. So this vertical distance, this one, divided by this one, tells you the average increment of f for 1 unit of increment of y in the interval x0, x0 plus h. Now I will repeat it again, okay? Don't be scared. So go back to average growth rate. We read what I wrote and I explain again. Okay. So you see, I wrote delta y0, but if you remember, delta y0 is also delta f of x0, divided delta x0. Delta x0 is h, okay, is the length of the change. And here I wrote everything. No, so I wrote everything. So it's very, you have everything here. I wrote fx0 plus delta x0, or fx0 plus h, if you want, minus f of x0, which is the change in the value of your function as if you increase x0 of what? Of an interval of length delta x0, which can be also called as h, divided the length of the increment, which is delta x0. So this is exactly what I told you before. Is m the slope of the secant passing through the point x0, f of x0, and the point x0 plus delta x0 and f of x0 plus delta x0. Exactly the one I have shown you just now graphically. And what is it? This is the average growth rate of your function relative to the point x0 and the increment of length h. What does this mean, average growth rate? It is the average increment of the value of your function for an increment of 1 unit of x, starting from the point x0 and considering an increment of length h. So I repeat, this quantity, you read it on your function, divided the length of the increment is the slope of the secant. And what does represent? The average growth rate of your function relative to the point x0 and the increment delta x0 or increment of length h, which is the same. Okay, that is, it measures the increment in the value of your function, the average increment, sorry, in the value of your function for the increment of 1 unit of x0, x starting from x0 in the interval x0 plus h. Okay, so it's an average increment. So if you multiply, I told you, this average increment that you call m times delta x0, what you get? The effective change in the value of your function as x passes from x0 to x0 plus h. So this average growth rate, f prime of x0, we have discussed it already, is the derivative of a function evaluated at x0, is the slope of the tangent evaluated at x0. So is the instantaneous growth rate evaluated at x0. That is, I repeat what I told you already before, and I wrote it. Is instantaneous growth rate at x0. That is, it is the estimated increment in the value of the function as x passes from x0 to x0 plus 1. So it's the estimated increment in the value of the function for 1 unit of increment of x starting from x0. Increment measured along the tangent line to the graph of your function at x0. Another thing is the relative instantaneous growth rate, which is the instantaneous growth rate at x0, that is the derivative at x0, divided by the value of the function at x0. This is relative because this should be a percentual number, because you see is the estimated increment on the value of y for the increment of 1 unit of x divided by what? The value of your function. So is the increment divided by the value of your function. So is a relative increment. So in particular is the relative instantaneous growth rate. It is the relative instantaneous increment of y due to a change of 1 unit of x at x0 approximated by means of the TG tangent line. Okay, because this is estimated through the tangent line. And furthermore, finally we have the elasticity of your function at the point x0. The elasticity, guys, is defined in this way, is f prime of x0 divided f of x0. Remember, this is the instantaneous growth rate. This ratio is the relative instantaneous growth rate. So if you multiply the relative instantaneous growth rate at x0 times x0 itself, you get the so-called elasticity of the function at x0. Which is the meaning of elasticity? It is the relative increment of y, that is of your function, due to a change of 1%, so it's different, due to a change of 1% of x at x equal to x0, estimated again using the tangent line to the graph of your function. So this is the relative increment, percentual means the relative increment in the value of your function due to the increment of 1%, not of 1 unit, of 1% of x starting at the point x equal to x0. So you go from x0 to x0 times 1%, okay? So these are very fundamental concepts. So review the graph. So average growth rate, and are useful if you look at the graph. So the average growth rate, the instantaneous growth rate, its meaning, the relative instantaneous growth rate, and the elasticity at x0. Okay, guys, since we need to start differentiation rule, I'm saying that maybe we can stop now. In the afternoon, we are going to see differentiation rules, and then we will do exercises. These differentiation rules, then we will do this exercise. Let me finish to explain something only, not about theory. Here we will do these examples together. Together we do this example. Unfortunately, you see, sometimes I say the past changes, and so you have everything colored sometimes. We will do this example this afternoon. Okay, also this example, we will do everything. As you see, there are only examples. We will skip for the moment indeterminate form because it's related to limit, maybe. And finally, guys, for home, if you are not able to compute derivative, I really recommend to do these exercises, because here I wrote so many exercises. Let me see. Different kind of exercises, find the tangent, compute the derivative. So you can, you can really do all these exercises. You can avoid the exercises on limits because we haven't done them together, but all the other exercises can be done. This after we will see. And for all the exercise, guys, you have the complete solution with all the steps, so you can really learn if you have troubles when you review it by making, after having studied, by making practice. So I stop now. So you understood that at the end of every presentation I gave you, except for the simplest one, the beginning, all the next one have a lot of exercises at the end, and all the exercises contain the complete solution with all the steps. So really, if you have trouble now or in the future, you forget something, you can take these notes and you can look, you can make practice. Suppose at a certain point you realize that you have still trouble with derivative. If you have no time now to do derivatives, in the future take them and do them to make practice, because you have, I repeat, all the steps, so you can check really everything. Okay, guys, so sorry, you can go because you are tired now. Okay, questions, guys? Guys, no, I said that you can go, guys. Are you still alive?
Yes,
Okay,
we
thank
are.
you.
Oh,
Yes,
you can
okay,
Yes.
thank you.
Thank you. Bye, guys.
you
Have a good
later.
lunch.
Thank you.
If you have
Thank you.
questions,
Bye.
thank you. Bye, guys. If you have questions, you can
Thank
ask me.
you.
Thank you. Bye,
Bye,
guys.
sir.
Thank you. Thank you. So I stop the recording now.